Imagine lying in the grass on a clear night looking up at the sky. You see thousands of stars, and you might even see the Milky Way galaxy. But it's what you can't see that holds one of the greatest mysteries of physics today. Everywhere in space, there's an invisible substance, and although it makes up 85% of the mass of the universe, physicists have no idea what it is. All we know is that its mass is like gravitational glue, keeping the Milky Way from ripping itself apart. We call it dark matter. In my research, I'm working to unravel the mysteries of dark matter and complete our understanding of the universe. My hypothesis for dark matter is inspired by the 15% of the universe we do understand, regular matter, like stars and people, which are composed of protons, neutrons, and electrons. A little known fact is that most of the mass of every object you've ever touched actually comes from the energy between particles. Einstein's famous equation, E=mc², tells us that energy and mass are really the same. Tiny particles called quarks are hiding inside protons and neutrons, as you can see in the middle of this slide. And the energy between the quarks makes up nearly all of the mass. But how does dark matter get its mass? To answer that question, I'm exploring a hypothetical model called stealth dark matter, where particles that we call stealth quarks are hiding inside the dark matter particles that we call stealth neutrons. So dark matter gets its mass just like regular matter. But in order to be a good candidate for dark matter, it has to be invisible to our telescopes. So in this model, the stealth quarks are arranged in perfect symmetry inside the stealth neutrons. And due to underlying physical principles, this symmetry makes them transparent and almost completely undetectable. In order to test this model, I'm using supercomputers to simulate stealth dark matter and make predictions. So far, astronomers have observed that dark matter doesn't seem to interact directly with regular matter or with itself. This is really weird behavior compared to our world of regular matter, where you can't just walk through walls because particles stick together. But dark matter is different, and my simulations will determine exactly how much stealth neutrons interact and stick together. In order to do this, I simulate two stealth neutrons in close proximity, as you can see on the right-hand side of this slide. And if I find that the two dark matter particles interact and stick together even a little, that would have a big impact on the shape of dark matter in a galaxy. And since dark matter is like gravitational glue, astronomers can look at the shapes of galaxies and determine how much dark matter is interacting with itself, and determine whether dark matter could really be made of stealth neutrons. Using theoretical physics, combined with the power of today's fastest supercomputers, I'm discovering the truth about dark matter. My findings will give insight into the question humans have been asking every night since the dawn of time: what's out there?